The titration curves, we did talk about titration curves on Monday, but they were titration curves of strong acid, strong base titrations. So now you need to know, a real common question would be to like explain the difference between a strong acid titration curve and a weak acid titration curve. So this would be weak acid with a strong base. Oops. The general idea is the same. The curve is basically the same. There are some key differences. Okay, so on a titration curve, pH is on the y-axis. If I'm titrating a weak acid, that means I have the weak acid in the beaker, and then the strong base is what I'm adding. So this would be the volume of base added.
This was there, but this is you printed for the versions. Here, I'll give one. Well, no, it's not give one.
Okay, I'll do it. Okay.
Another time.
Okay, the difference though is that the starting pH is going to be higher, okay, because if you think about you're titrating a weak acid pH is going to be higher than a strong acid pH. The strong acid pH curve is going to start lower on the pH scale. Okay, so you start higher up, and then you have the same kind of shape, that little curvy shape. This steep line portion is not as steep and not as big, but you still kind of have the section where the pH increases rapidly. The middle of that section still represents the equivalence point. The only difference with that you need to know is that the equivalence point pH is greater than 7 when you're titrating a weak acid. The other thing, a real common multiple choice question is they'll have like one of these graphs and they'll have them labeled with different letters and stuff, and then they'll ask you which section represents the buffered region of the titration. Well, the buffered region, you know, when you can use that Henderson-Hasselbalch equation, is before the equivalence point. If the equivalence point is right here, this area right here represents the buffered region, which is what they call it, which just means that the solution that is made when those things are mixed together is a buffer. So that's all. For this next one, I'm not actually going to do this example because the process is the same and the calculations and the way you do the calculations is the same. The difference is just the equation. Okay, so if you want to, instead of just writing out this whole thing, just write down NH3 and HCl. Because when you have NH3 in the beaker and you add HCl to it, hydrochloric acid ionizes. Okay, the chloride ions don't matter. So then your reaction that you have going on in the beaker is NH3 plus H plus, and it gives you NH4 plus. And so just the writing of the equation is a little bit different when you're titrating a weak base instead of a weak acid. And then you do the whole, you do the millimoles thing, you set up your BCA table. Before the equivalence point, it's a buffer still. At the equivalence point, you've got to do the 2 steps. And then beyond the equivalence point, it's going to be a strong acid instead of a strong base. So the process is still the same. You follow the same steps as the other one. All right, we're almost done. Okay. You ready? Apparently I got rid of letter C, whatever that was. And then I'm also skipping, I talked earlier in your notes, we talked about finding the ratio. So, you know that whole, in the Henderson-Hasselbalch equation when you solve for the B over A, we've done that lots of times. So we're skipping that and going straight to F. And this thing right here is another like big idea of chapter 15. I'll let you write it down, and then I'm going to talk about why it's a big idea and how you figure it out from the graph.
pH minus pKa?
pH equals pKa. Okay, half the equivalence point. At half the equivalence point, the pH is equal to the pKa. Why is that important? If you have one of those titration curves, then if you can figure out where half the equivalence point is, we'll look at that in just a minute, you can figure out then the Ka of the acid based on the pH value, and you can identify what that acid is if you don't know it. So if this is your pH curve, like this, and this is my equivalence point, right here. If my equivalence point is at 40 milliliters, then half the equivalence point would be at how many milliliters? 20. Okay, half of that by volume. Okay, you don't have to try and like figure out with your eyes what's halfway between. Just go to the halfway milliliter mark. Okay, so at 20 milliliters, this would be half the equivalence point right here. And at half the equivalence point, you can figure out what the pH is based on the graph at that point. And if you can find out what the pH is, you would have a number here. And then you would know that that would equal the negative log of the Ka value. And then you could figure out what the Ka value is. Now, how do I know that? I also am just going to prove to you, I know that's what you want me to do, right? Is to prove to you that pH equals pKa at half the equivalence point. If I set up my equation, okay, HA represents weak acid, hydrogen ion, some anion, okay? And then if I add hydroxide ions to it, I get water, and I get whatever the anion is. If I start out with 5 millimoles of the weak acid, at the equivalence point, it would be 5 and 5. So half the equivalence point would be 2.5. Right here, okay? I have half the amount of millimoles of the base. So then if I do my whole little table here and I subtract 2.5 and get 0, subtract 2.5 and get 2.5 right here, and then I do 0 plus 2.5. Okay, what I'm left with, and this is before the equivalence point, so I'm left with the buffer. I'm left with the weak acid and I'm left with the conjugate base. Those have equal concentrations or equal number of millimoles at that point. So when I plug it into this equation, pH equals pKa plus the log of base over acid. Base over acid is 2.5 over 2.5. That's just 1. What's the log of 1? The log of 1 is 0. Okay? So the pH equals the pKa at half the equivalence point. All right, next, polyprotic acids. Do you know what polyprotic means? What did poly means? Many. Protic, protons. Let's say between like HF and H2SO4. Hydrofluoric and sulfuric acid. Which one is the polyprotic acid? H2SO4. Why? Because there's more than one hydrogen. So any acid that has more than one hydrogen is called a polyprotic acid. All you really need to know about that is the shape of the titration curve if you titrate a polyprotic acid. It actually, you'll have one little curve with one equivalence point for the first hydrogen, Okay, so it'll like neutralize one of the hydrogens first, and then it neutralizes the second hydrogen. And so you get kind of two pH curves kind of put together. Because for H2SO4, when it gets rid of one hydrogen, becomes HSO4 minus. So that titration happens first, and then when that is done, then it titrates the second one and gets rid of the other hydrogen, and you get just SO4 2 minus. So it kind of goes in steps, one hydrogen at a time. That's all you need to know about that. One more thing. You don't need to write this. We've talked about this earlier. You need to know this because it will ask you, and this is the very last thing, some questions on your homework. There's lots of different indicators that can be used to figure out equivalence points when you're doing a titration. And so they might give you like lots of indicators to choose from, and you have to pick an indicator that would be a good one to indicate the equivalence point. So there's a couple ways to do that. Make sure you write down that page number too, because on your homework you're going to need to refer to that chart on page 715. If you have the titration curve, this little thing, and you know the pH at the equivalence point, then you can use the chart on page 715 to figure out which indicator would be the best. And when they say which indicator would be the best, they mean the one that changes color at the right pH value. So like, we did the titration when last year where it went from clear to pink. And we wanted it to change color at the right place, so you know that that's the point of neutralization. That's the equivalence point. So if you know the pH at the equivalence point, then on page 715, there's this little diagram, or this little chart that looks like this. It shows you all the different indicators and what color changes they go through in an acidic pH and a basic pH. And they show you all these little bars kind of represent the pH where they change color. So all the ones over here, this indicator over here changes color at pH 1 and so on. So if you're looking for something that changes color at pH 7, then you would go over to 7 and see which indicators change color at that pH. And then you could choose that as an indicator. Now indicators are slightly acidic on their own, which is why if you add too much of it, it can mess up your results during a lab or whatever. And so if they give you the Ka values of indicators, if you pKa that, so negative log the Ka value, whichever one has the closest value to the pH at the equivalence point would be a good choice. So it kind of depends on what data they give you. If they give you the graph, then you can use the chart on page 715. If they give you a list of Ka values, then you just negative log them, kind of like you did on your lab. And then you can figure out which one has the pKa closest to the pH value. And then that's a good indicator to use.